Hey guys, so my name's Tavian. I'm gonna start doing some coding reviews and some coding explanations. Just let me know down in the comments what you guys would like to see. Right now I'm gonna do a little walkthrough of my RSA implementation in JavaScript. So the point of this project is to like work towards a better solution. So I'm making a project called Quarks, and what Quarks is it's my own encryption system that is meant to go and combat against quantum supremacy. Quantum supremacy, if you don't know, is the idea that quantum computers become better than our best supercomputers in binary known today. And what this problem could cause is they could implement things like Shor's algorithm, and Shor's algorithm uses quantum computing to defeat RSA and decrypt it in a matter of minutes or even days maybe, which is still very, very insecure because oftentimes RSA keys don't change, and RSA is a big encryption system that's used in many things like blockchain and for everyday messaging, emails, stuff like that. So it would be a very big problem if quantum computing defeated that, especially for national security. So my idea was to take Quarks and make it better than RSA. I'm going to implement things from RSA, but it's going to be completely different. That'll be for another video though. Quarks is not finished yet. The mathematics for it is working and it works well, but I still need to implement it, and I'm planning on implementing it in JavaScript so that I can have a full browser version working. Obviously it won't be ready for production because this JavaScript obviously doesn't allow for such large calculations. And if you are familiar with RSA uses numbers that are thousands of digits long or 100 digits long, right? So JavaScript would have a hard time computing that. So I'm going to get into the code here and explain function by function, probably not line by line, but I'll try my best to break it down. So I'm using this package called BigInt and BigInt crypto utils. These are basically to make it so that I can implement faster things, and I can also implement like bigger calculations so that I can make somewhat good keys without having to like cost any time for computing. So we see that we're starting out with this multiplicative inverse, and what that does is it calculates the D in RSA. And if you're familiar with RSA, it looks something like this. You're doing a calculation where you take the two random prime numbers that are usually very large, but in our case we're going to make them small, and we'll take P and Q are going to be our prime numbers. And what we do is we do P times Q to equal N. And what this does is it's very hard for a computer to reverse this multiplication of two very large prime numbers, but it's very easy for it to create it. So when we create this variable n, then we can take the variable n, and there's this cool modular arithmetic where you can go and say, you can take something that is coprime to n, and you can say n to the power of e is and you take that to the mod of n. Sorry. You take the message to the power of e. So the message is just a character in the alphabet converted to ASCII numerical values. So for example, n is 72. And so you would take the number 72 to the power of e mod n to equal the encrypted message. And we will call that C. Now we can take this this crypto value that you're sending over the internet, And the person who created the private key can just say c to the power of d, which is our private key, mod n equals the message. Now, how you get d is you take, that's where this multiplicative inverse comes in. You take the multiplicative inverse of e and the phi of n. And you can find the phi of n by doing p minus 1 times q minus 1. That's an easy way to do it. But no one's supposed to know what p and q are unless you're the private key holder. The private key holder is the one who creates the keys. He sends the public key out so that someone can encrypt data and send it back to him securely, and then so anybody can know the public key, and then he decrypts it with his private key. So we take this multiplicative inverse and we apply it. I'm not going to get into the mathematics of it, but this finds the multiplicative inverse of those two things. And just to clarify, phi is a mathematical component that basically just says how many numbers beneath the number that I'm taking the phi of, how many numbers beneath that are divisible by it, basically. So, and then obviously this is just a prime. It's just a function to check if it's prime or not. That's just to make sure that the user is inputting two prime numbers for p and q. Then we're going to get into this generating the key pair. This is where it gets juicy. So we're basically saying, right, we're saying if p is prime and q is prime, then we can say we can, if it's not prime, if either of them are not prime, it throws this error that both numbers must be prime, and if they are equal to each other, it throws the error that the two numbers can't be equal, right? And then we're just saying, okay, we want this variable n to equal p times q, and we went over that earlier. And then we're taking phi, which is p minus 1 times q minus 1. And when you're working with two prime numbers, it's very easy to calculate that because you do p minus 1 times q minus 1, because there's no other numbers that are divisible by that prime output. I like to call them secondary primes. So when you multiply two prime numbers together, that number can only be divisible by those two prime numbers. So it makes phi a very easy calculation if you know those two prime numbers. And we can say, so here we're taking e, and we are calculating e and making sure that it is coprime to n, so that we can calculate a correct number that we can find d with. Here we're finding the greatest common divisor using our plugin above with big ints, and that is going to help us derive d. Okay, so we take this variable g and we're saying, okay, we want to find the greatest common divisor of e and the phi of n, right? And the purpose of doing this is so that we can find that they are coprime. If the greatest common divisor is 1, then obviously we get, well, not obviously, but that's how we get that e is coprime, and that we can find a correlating d. And that's where we take this multiplicative inverse and we find the inverse by doing e, I think it's d times e is equal to 1 to the mod of phi n. It's very complicated. And then we're returning our two public and private keys right here. And this will all be on GitHub, so you can look at it if you want to. So yeah. Okay, now we're going to look at this function called encrypt. In this function, we're going to take the function and we're going to give it the argument pk. pk is going to represent the public key, and it'll have two values as seen here. We're going to have e and we're going to have n. And this is what anybody can know, and this is how you encrypt the data, right? So we're going to give, we're giving e first, so we're going to be passing this to encrypt, right? So we're going to set our key equal to E. So PK, the 0th in this list. So we see that E is the first one in this list, and so now our key is E. And then we're going to take N, and we're going to get N by doing the second thing in the list right here, and public key. Now we're going to take this plain text, and we're going to use that to essentially generate the ciphertext. So I'm just setting the ciphertext here, and what I'm going to be doing is I'm going to be breaking up each character that the user types in, and I'm going to convert it to ASCII code. So I'm going to convert it into a numerical value for the ASCII text. And then I can take this cipher and I can basically go through each character, and that's what I'm doing. I'm going through each character in this string that the user puts in, and I'm saying, okay, I want to put inside the cipher array or list. We're gonna push or append for every time it goes through. We're gonna append the encrypted value of that letter. So right here we're saying, okay, we're gonna call it a big int, and this is where we use the big int crypto utils, and we say .mod power. Okay, now we're gonna use this mod.pow or .modpow, which implements the modular exponentiation. And modular exponentiation basically says, like, instead of going through and doing like 3 to the power of 200, that's really hard for a computer to do compared to like saying, okay, we do 3 to the power of 2 and then mod whatever number we need to mod, and then we do the output of that to the power of 2, and we keep going and we break it up into bits. I'll leave a link down in the description of a good tutorial for learning what modular exponentiation really does, and we're going to use that to output this a lot quicker than it would be if we just did it with straight math. So we're going to say for each character, we're going to encode it, so char code at I, which is our variable here. So this is just representing the character, and we're going to turn it into the numerical value of representation of the ASCII text. And then we're going to take it to the power of the key, which is E. And then we're going to take that to the mod of N, that output. And then we're gonna set that to a string for big int, because big int processes better with strings. And so then we have this big integer where we can console log this cipher after we get all of the letters encrypted and in the cipher list. I'm just console logging it so you can see it. And then we're returning the cipher for the function. So now that we have this encrypted data, we can decrypt it now. So this is our ciphertext, that's where this comes from. So this is when the end user that made the private key is getting information from the person that encrypted data. So I'm saying cipher is ciphertext in this function. And then this stands for private key this time. And same as up here, we're going to get D and N. So instead of E, we're going to get D. So D and N are going to be put in here, and we're going to set D to the key, and we're going to set N to N, obviously. And then we're going to set a string, an empty string for plain, and this is standing for plain text. So this is, we're decrypting the data now, so we're going to get the plain text of the decrypted data. And we're doing the same thing. We're going through the cipher list, or the ciphertext list, and we're going through each item. That's what I stands for. And we're saying that this plain text is equal to the string that it outputs plus the next string plus the next string every time we go through this for loop. So we're saying plus equals for the string. So we're turning this character into a string. So we're saying string from char code, and we're basically saying that's the inverse of this function up here where we're converting it to the character code. Now we're reversing it from the character code back to a string, right? And obviously we need to decrypt it first. So inside of that, we're going to decrypt it. So we're going to turn it into an integer. We're going to turn the big int into an integer so that it can execute this function properly. So that's why this parse int is here. And we're going to say big int of this. So now we're going to do the modular exponentiation again, except this time with d in place. And obviously this runs a lot faster so that we don't run into problems with computing time. And again, I'll leave down in the description, I'll leave down a link to a good tutorial for that. So we're taking the ciphertext, the character in that ciphertext, and this will be encrypted right now. And we're converting that to a string. Okay? And then because these big integer NPM packages work a lot better with strings than with integers, so that's why I'm doing that. And then I'm taking this key and I'm doing it, so I'm taking the ciphertext and I'm taking it to the power of d, which is the key. And then I'm taking that to the mod of n, which is just n. And that will output the, so say n was our encrypted letter. Let's say we just had one encrypted letter. Or let's say we had 5 n's. It would go through and it would say, okay, 72. It gets 72 from the cipher from this function here. And then we're parsing it into an integer to 72 instead of a big int value, which is a different data type. And then we're saying we want to turn that 72 back into a string. And so that's what this does. And then we can return this string now as plain. And so that's where we output it down here. We're saying our encrypted message is our output here, right? For encrypting the message right here. So encrypted message, encrypt, and then we're decrypting it here with that, and it outputs, we're console logging it, so it outputs our original message. So let's run it here. And I preset the values because I didn't make any HTML for it or anything, and I didn't want to implement any like input statements or anything because it's actually quite buggy in JavaScript. But if I wanted to, I could make like an HTML template to pass these input values into it, but I just did my own. I put my name in here for the message, and I chose pretty big prime numbers for my keys here. And obviously there's a cap to how big of the prime numbers can get because JavaScript can't compute such large numbers. So this is about as large as it gets for this implementation. And that's because this is only for example really. And this is where I'm gonna do like a beta test of my encryption system with Quarks. And that'll be for another video. So now we're gonna run this and we see that we get all of these outputs, right? So we're saying our public key is this is our E, this is our N, and this is our D, and again this is our N in our private key. And then we see that we're converting all of those characters into ciphertext here, and we're outputting that. So now we've got this encrypted message here. This is what we'd be sending over the internet. And then when the person on the other end gets this encrypted message with the private key, they're decrypting it with the private key. That should say private. I'll fix that. And so we're doing the encrypted message to the power of D mod n, and that will, well, not the encrypted message. We're taking each point of it and encrypting it, right? And that's this list right here. I just joined this right here, as you can see right here. We joined it so that we could see what it would look like. So it would be this list, and we decrypt each letter, and we get that our message is Tavian. That's my RSA implementation in JavaScript. That was kind of rough. I'm sorry if you couldn't follow. Let me know what other tutorials you guys would like, and let me know if you want me to do this one again, because this was a really rough one and I haven't ever done this before, so I'm not sure I'm not sure how well you guys will be able to follow with this. I can do it again and slow down a bit, and you guys can ask questions and I can address those questions, and I can show you more in depth of modular exponentiation in my own words, and I can slow that down a bit. But yeah, this is the basic idea, and I'm going to go into quarks next time as well when I get that implemented. Yeah, thank you.